So again, inverses, this is just doing algebra 2 inverses, nothing crazy, nothing calculus here. Remember the big idea with inverse is that we switch x and y. If we think of the graph, this is also when we reflect it across the line y equal to x. Now you can see the functions that we're working with are e to the x and natural log of x. Our e to the x graph looks like this. Goes through the point 0, 1. And my natural log of x graph looks like this. And goes through the point 1, 0. So we can see x and y values flip-flop. Also, that graph is reflected across that line.
So for number 1, we like make them both ln.
Hold on, we're going to go over it. So again, inverses, we're switching x and y. Now, since we're switching x and y, what happens is that your domain and range get switched as well. So whatever was domain of your original function will become the range of your inverse function. And likewise with the range. Whatever was the range will become the domain. Alright, so again, we want to switch x and y. Typically, it's easier to just go and rewrite this as y equals, rather than having to write the inverse notation over and over again. So the big idea is to flip-flop those. Now we need to solve for that y, so that we can have that function notation. But our y is trapped up in that exponent. So how do I undo the e so I can get my y out of the exponent? Yeah, we have to natural log both sides. E and natural log are inverse operations. As we can see up here, they're inverse functions as well. So to undo e, we need to do natural log of both sides. So natural log of x equals the natural log of e to the y minus 3. So I have natural log of x equals, what happens with my natural log of e here? Yeah, they undo each other. It's just like doing squared and squared, they undo each other. Or when you have a positive number, you subtract it, you're undoing those operations there. So we're left with just y minus 3. Questions what I've done so far? Logan, are you with me? Okay. So when you took algebra 2, you might have just thought that you were rewriting it, going from here to here. That's fine. You can skip that middle step if you're able to do that mentally. But when you were rewriting, what you were technically doing was taking the natural log of those steps. If this was a base of 2, what would I do instead of natural log? Log base 2, yeah. So your base needs to match. So why am I doing natural log and not log base e? Because log base e is natural log. Good. Okay, so we have y equals natural log of x plus 3. But we do need to make sure we use proper notation. Since we start with f of x, we need to finish with f inverse of x. This indicates that we're dealing with the inverse function. And I'm going to go and write my 3 first, just so you don't think that it's part of that natural log. Alright, so that's our inverse. Questions on that? Yeah, we're about to. But do we have questions before we talk about this? Okay. So we can see that our function here is natural log. So what is my domain of natural log of x? What did you say? Careful, we want domain. Domain of natural log. What's my domain of natural log? 0 to infinity. Now, do I include that 0? No. No, who had that asymptote there? How does this 3 affect my graph? Yeah, it just shifts it up, so it doesn't affect my domain at all. Also, if we would have taken a look at our original function, e to the x minus 3, what happens with this graph? What transformation's going on? Right, 3. So we would have something like this. What is my range of this function? 0 to infinity, and notice that is my domain down here. So again, what was my range is now my domain. Alright, questions with one as a whole? No, it just said state its domain, so it wasn't necessary to do so. Alright, so with number 2, same idea, we're switching x and y. Alright, I need to get this y by itself, so first I need to get natural log by itself, so x plus 3 equals natural log of y plus 2. My y is stuck inside that natural log. How do I undo natural log? So does anyone remember the proper phrase for doing e to both sides? called exponentiating. I think it sounds pretty cool because it sounds really intense, but it's not that crazy. So we're going to exponentiate each side, which means we are taking these and making them exponents of the same base. I'm choosing a base of e. Why am I choosing my base to be e? Right, because again, we want it to have the same base as my log. Alright, so I then have e to the x plus 3. What happens with the e natural log here? Yeah, they undo each other, so we're left with just y plus 2. And then I have y equals e to the x plus 3 minus 2. Now again, we want to make sure it's proper notation. We start off with y, so our notation would be y inverse. So this is our function here, and then we'll deal with domain in just a moment. Questions on that before we talk about it? Okay. So again, my original e to the x graph looks like this blue one up here. But we have some transformations happening. What is this negative 2 doing to it? Good. So instead of having a horizontal asymptote at 0, we'll have a horizontal asymptote here. And what is this x plus 3 do to my graph? Right there. Alright, so let's see, this point 0, 1 is going to go right 3 and down 2. Alright, so it's something like this. Did those transformations affect my domain? No, what is my domain? Yeah, negative infinity, positive infinity. Which, if we think back up to our original function here, this natural log of x plus 2 minus 3, we get shifted left 2 and down 3. What is my range of this one? What's the range of that natural log graph? Anything positive infinity, which we can see is our domain. Alright, questions with all that? Okay, just kind of a refresher. Alright, let's go and take a look at some of these questions on our homework. Yes, I'm sorry. Oh, we're going left 3, thank you. Well, let me move it. Oh, how convenient is that? Yeah, guys, for our inverse graph here, we were going left 3. Still doesn't affect our domain, but yes, you're correct. Thank you. Just not worth it right now. Alright, give me a moment to go and bring up our answer key for that. Come on, computer, you can do it. Alright, so let's go take a look at 17 first here. I'm not going to go over 16 yet since that was an even. We will come to that later. Alright, so 17, I'm assuming this is the 17 we wanted?
Yeah, the other 17.
Okay. So we have this function here. It says find the slope at the point where it crosses the x-axis. Any function that crosses the x-axis is going to be where my y value is 0. Alright, so where it crosses the x-axis is where my function is 0. So that's what's happening over here. And we see that occurs at x equal to 0. So what I'm really trying to find is my derivative, the slope, at x equal to 0. So when I do my derivative, I get negative e to the x, and then the derivative at 0 is just negative 1. Alright, so then find the equation that tangent the curve at this point. So you need an a for part b. So we need a point in the slope. We know that our slope is negative 1 from what we just found. And we have our x value is 0. What's the y value that goes with that? 0, yeah, that's what I used. We were trying to find what's the x value and y is 0. So we have the point 0, 0. and our slope was -1 from our problem before. So compile that all together. You, again, can leave it in this point slope form, so y minus 3 equals -1 times x minus 3. That would have been -4. Alright, then find the equation of the line normal to the curve. So normal just simply means I need to take my slope and do opposite reciprocal. So if my slope is -1, my new slope is +1. Again, we're using the same point because it's set at this point. So then you could, again, y minus 0 equals 1 times x minus 0. Questions on that? Where were we getting stuck with that one? The whole thing. So was it the fact that this is where it crosses the x-axis?
I personally just messed up on either the x.
The derivative? Okay.
I put either.
So make sure you know your derivatives, but think about what it means. Crosses the x-axis. What does that tell us about our function? We know that's a 0 or y is 0. Alright. Let's see what else we have. Am I missing it? Oh, the 21 that said omit. So omit 21. Don't worry about that one. So we check your answers with the key. Okay, but let's take a look at 50. I feel betrayed. The key was up on Blackboard for you to check. Okay, so 15 here we had implicit. We have to do product rule with this first piece. Alright, so we have to do product rule with this first piece. Second stays through the first, plus first stays through a second. Don't forget your dy dx. And then we have derivative -2x, which is -2. Derivative this is -3 dy dx. Don't forget that. Alright, so we want to take these pieces and move them over to their side, so we get that -e to the y and that +2. And then factoring out our dy dx's, we're left with e to the x, or sorry, x times e to the y minus the 3 there, and divide those. Questions with that? Okay. And it looks like 31 in our natural logs. Actually, let's go 23 first, since we'll hit that on the way. Okay, so with 23 here, you could have done quotient rule, but it's going to be easier for you if you go and multiply the x over and do product rule. Now, if you do quotient rule, you end up with, get it for you. You end up with something that looks like it's a different answer, but it's actually saying just an algebraic manipulation. Alright. So if you were to do quotient rule, you would have ended with x squared plus natural log of y over x over y minus x squared. But we can't have those complex fractions, so just like here, to get rid of that complex fraction, again, we know that we can get a common denominator and then multiply by the reciprocal. Earlier, we talked about a much quicker way, is just multiplying by that denominator that's causing you issues. So same thing up here, so I'm going to go ahead and multiply by that denominator of y over y. And we end up with, let's see, we've got x squared y plus y natural log of y over x minus x squared y. So if you did quotient rule, you would have gotten this. Now this and this are actually equivalent. And we'll talk about why. The questions on how to get to either of these answers using either the product or the quotient.
I mean, for mine, I just refactored out the, well, for the, I did quotient, but I just factored out the x and the y.
And wrote it next to it.
Yeah.
That's fine if you had two fractions multiplied together. Okay, so these look pretty different, right? But they're actually the same thing. So let's take a look at this. For this particular problem, they're the same thing here. I see this natural log line. Notice there is absolutely no natural logs here. So let's take a look at trying to get rid of that. If I go back up to my original equation and solve for natural log of y, and natural log of y is x squared plus y times x. Do you guys agree with that? Are we okay with that? Okay, so now I'm just going to make that substitution in here, because that's what natural log of y in this problem is defined as. So I have times x squared plus xy. And now when we go through and simplify, we'll find that it's the same thing here. So I'm going to go ahead and multiply my y out. So I have x squared y plus x squared y plus xy squared over x minus x squared y. I have x squared y and x squared y, so that's going to be equivalent to 2x squared y plus xy squared. Notice how we are much closer now? Thoughts on what I can do to get it to be the same? Yeah, take out x on the top and bottom. We can see that everything has an additional x over there than it does over here. So if I go and take out that x on top, then I have 2xy plus y squared. Take out an x on the bottom. So I have 1 minus x squared y. And what happens with these x's here? Yeah, they reduce down to 1. So I have now 2xy, same thing, plus y squared, and 1 minus x. Oh, I forgot, that should be a 1. So if you did quotient rule and you ended up with this answer that had the natural log in it here, you actually have the correct answer. It's not that you did something wrong. It's just that these are equivalent after a little bit of algebraic manipulation. So if you did quotient rule, got that, you still got the same thing. For response, it would not matter. Multiple choice, they could have this method instead of that one. So just be mindful of that. Again, multiplying the x over is going to make it a lot easier to work with. So I would recommend going. All right, questions with that 23. And let's go 29. Yes, 29, our chain rule. Alright, so 29, we have h of x is made up of f of g of x. It is a composition of functions, which means when we do our derivative, we must do the chain rule. So our chain rule says that doing the derivative of the composition, do the derivative of the outside, inside stays, and I have to follow chain rule and multiply by the derivative of the inside. That's what you see here. But we only care what the derivative is at pi over 4. So then you take pi over 4, substitute it into this expression here. So I need g of pi over 4. So g of pi over 4 was just 0. And then g prime of pi over 4, so you did have to find your derivative here. And g prime at pi over 4 was negative 2. So then we have f prime of 0 times negative 2, so you need to also do your derivative for f. And f prime at 0 is 1. So then we have our 1 times negative 2. So remember, composition of functions is just simply chain rule. Derivative the outside, inside stays, times the derivative of the inside. Alright, questions with that? Okay. Now 31.
So let me guess. Can I try solving it, please?
29?
31.
Sure. So 31, we are doing integration with these today. So 31 is just to see if you could try to get that. Today we're going to be learning how to actually do it.
So let me guess. So I got an e set.
Great question.
So yeah.
It appears that it is E.
Because like, so you look at e, get to the take the exponent,
we're
the
caught up
exponent,
now.
multiply.
Okay.
We just take the derivative of the exponent and
So with 31, we see we have an e function here, and there is an inside piece to that. So we know that when we do the derivative, we're going to have chain rule fall there, and if we do a chain rule, then we are going to end up with that x there. But again, this is what we're learning today, but wanted to give you a shot at trying to figure it out, especially since it's multiple choice. You could have also gone there and done the derivative,
yeah, but I did
and then see what matches up with what's inside your thing.
what I did was just work from the back.
Yeah,
So
that's
the
fine.
answer is like multiply it and
Alright, so again, today what we're doing is actually what 31 is there. So let's go and take a look at our notes for Did you do something to him? Because you just had this mischievous look.
What?
You do have to be careful.
I found something bad about having this waterload one. Sometimes, like, after you leave it sitting for a long time, I open it, and then the water just starts spraying out of the straw.
Yes, if you leave it in the hot part and you open up and it squirts out and sprays
Yeah. I just love it.
water bottle. Alright. Is there anyone that did not get a copy of this? Okay. Alright, so in last class we learned about derivatives of exponentials and derivatives of natural log. And today we're gonna be learning about how to integrate functions that deal with exponentials and natural logs. So again, our new functions for this unit are exponentials and logs, and soon coming inverse trig. So we first started off with doing our derivatives for it, and now we're gonna do our integration. This isn't the right one. That's the one we just did. Alright, give me a moment. Where did it go? Steven. I know what it would be if it was up to me, but it's not up to me. I wouldn't go to school.
How?
Do you know?
Yeah, but they built 14 snow days into the school year, so they're making us come 14 more days than we really need to.
Do you know what actually happened with, like, the stuff today with the fire alarms? No.
Okay, so again, last class we learned about the derivative. And as we know, the derivative is essential to being able to do your integral, because when you integrate, you use the antiderivative. So we're dealing with exponentials for this piece. Last class we learned that if we have e to the x, my derivative is what? E to the x. Now, of course, we know if we have something more than x, we can follow a chain rule with it. But with that being said, if I have the integral of e to the x dx, what would that give us? Oh, good job with that plus c there. E to the x plus c. This is an indefinite integral, so we need to make sure we have that plus c as a part of it. Now, again, we know that if there is something more than x, we can't just simply say e to the x. But before we talk about that, what we're saying here is that if I were to take the derivative of this piece, I would get back to this function here, right? This is my antiderivative. And the antiderivative is defined as the function where when you take the derivative, it gives you the function that you're integrating. So if I had something more than just e to the x. For example, with number 1, I have e to the 5x. For number 3, e to the x squared. If I have something more than just x, I know that if it was the derivative, we'd have to do chain rule, but there's no chain rule for integrals. What do we have to do instead? There's something more than just x. Well done, Stephen. Use substitution. When we have a composition of functions in our integrals, we have to use use substitution to help us counteract that chain. All right, so let's go take a look at how that would appear for our ABX problems. So just make yourself a note. Use substitution still applies. And again, we use use substitution when we have a composition of functions. Alright. So for number 1 here, we're going to have a pretty easy use sum. We have e to the 5x dx. Again, we have something more than just x here. Now, you might be able to mentally kind of figure out what your antiderivative is going to be. But if I have my exponent is 5x, and let's go ahead and let u be that. So let u be 5x. 5x is my inside function. My outside function is e to the exponent. What would my du be? Dx. Good. Do I have a 5 represented here? Nope. So let's go and divide that over to the other side. So now when I go ahead and change this, we have the integral. This becomes e to the u, and dx is 1/5 to u. Just go ahead and bring that 1/5 out. Alright, so now our 1/5 just hangs out in front. What's the antiderivative of e to the u? E to the u, just e to the u. We don't have to do anything with our power there. So just e to u plus c. And we need to make sure our answer for indefinite integrals that we go and plug our u back in here. So we would have 1/5 e to the 5x plus c. Now technically we can go ahead and multiply out that 1/5, but what's 1/5 of some constant? Yeah, just a different constant. So if it was free response, and you were at 1/5 c, that'd be perfectly fine. But it's not necessary because again, c is just representing whatever constant is. Alright, so if we were to take the derivative of this, we'd have 1/5 times, the derivative would be e to the 5x times 5. And then our 1/5 and 5 would reduce, so we're left with just e to the 5x. Remember, you can always take the derivative of your antiderivative and see that it matches up with our function inside the integral. Questions with number 1? Okay. Now with number 1, we had a pretty small use up here. If you are able to mentally figure out, hey, if I did the derivative, I have to multiply by 5, so to counteract it, divide by 5 and jump straight to your answer. That's fine. It's a small use sub. If you're able to do that mentally without writing out the use sub, that's perfectly fine. If you need to do the use sub, though, by all means do so. Okay, so let's take a look at number 2. So for number 2 here, I have 4e to the 1 minus x. Once again, I have something more than just x in my exponent. So let's let u be that. Because again, e is my outside function. 1 minus x is my inside function. What would du be? -1 dx. Alright. This 4 is not a part of my du. Can I just bring it out in front? Am I allowed to take that 4 and bring it in front? Yeah. Why am I allowed to bring the 4 in front? Yeah, it's just a coefficient, it's just constants being multiplied by my function. For limits, derivatives, and integrals, we're allowed to bring that coefficient out front of that, outside in front of that operation. Alright, so then we have e to the u, and dx, well actually we have du equals negative dx, so let's rewrite that, because there's no negative. Alright, so dx is negative du. I'm going to go ahead and just bring that negative out as well. Are we all right with that? Okay, so now we go ahead and integrate. What is my antiderivative of e to the u? E to the u plus c. So we we have negative 4 e to the u is 1 minus x plus c. And again, if we were to differentiate that, we'd get back to that function in seconds. Okay, questions with that? So again, u sub is the same thing as before, just now we have a new function to work with. Alright, with number 4, what do you think we should let our u be? Alright, so if we let u be x squared, what would my derivative be? Right, d would be 2x dx. But I still have this issue here of 1 over x. And it doesn't cancel out with anything here. So although x squared was a good option, because that is in the denominator, it's not what's going to work best for us. What else could we try instead? Yeah, let's try that 1 over x. Let's see if that takes care of it. Because that is inside of our e dx function. Now, 2x squared was also an inside piece. So let's see how that goes. 1 over x, same thing as x, the negative first. And what's my derivative of that? Negative x, the negative second dx. Which is just negative 1 over x squared dx. Do I have x squared in the denominator represented? Yeah, I've got that x squared in the denominator dx. So we can see that our u, its derivative, is represented as well. Alright, I want you guys to go and finish out number 4, see what you get. Close your questions.
Did you take the negative out? You're taking the negative out.
So 1 over x is the derivative, you're correct. But we're not taking the derivative. Now, if it was just
Yeah.
you're listen to this thing, it's just a positive. So it's good that you're mixed, but it's not going to be Alright, so everyone should be working on number 4, see what you get. Alright, when we changed everything to be in terms of u, did we get a negative 1/2 sitting in front? Double check to make sure you have both the negative and the 2. We did not need this 2 that was in our denominator. It was not a part of my du. And it's just a coefficient, so I pulled out in front, but notice it's 1/2 in front because it's in their denominator. And when we did our du, our negative we didn't need as part of our x squared dx, so brought that out. Okay, so then we should have ended up with our answer of negative 1/2 e to the 1 over x plus. Questions on that? Are we okay with that? Did we get that? Okay. Try number 6. Talk with your shredder partner. What could we do with that? How could we go about that one? Let's calmly discuss number 6 with our
I can't think of anything. What is this factor? Never mind. I forgot what it is. I guess the 4x stuff.
Alright, so let's talk about possible options for this. Raise your hand if you said let u be 4x. Anyone go with that one? Raise your hand if you said let u be x. Okay, anyone go for factoring? Okay. If we did not say any of those, then what were other thoughts? Steven?
You split everything up there, and everything is over equal.
So splitting up the numerator of the denominator. Anyone else say something like that? Okay, other thoughts? So we had 3 people with thoughts in here. It's a little concerning. Gora?
Yes,
Let u equal e to the x. That's another one too. Good. All right, so let's investigate each of those. If we let u be 4x, then unfortunately it doesn't get us much further because we can only replace this here and nothing else. So although that sounds like a good option for this particular problem, it's not going to be beneficial for us. If we let u be x, then once again we're only able to replace a couple of these. Also, you're not really changing, you're not making it easier for yourself, you're just changing the variable to be from x to e. Nothing else has changed about the problem. So typically you never ever want to let u just be x because you're not really making the problem simple. Alright, so factoring. Let's talk about factoring. I got really excited thinking this was a factoring problem, and it almost is. But unfortunately we cannot factor this. If we take a look at this here and mimic this, we would have had to have our exponent here be 2x rather than 4x. If it was 4x, then our middle exponent should have been 2x to match up with it. So that by itself makes it so we cannot factor that. If it were a factoring problem, I don't think anything would have reduced with our denominator, so unfortunately that was not a method as well. Alright, and then if we let u be e to the x, again that gets us a little bit closer because we get a u there, a u there. But we're still left with that e to the 4x. So a good idea, but again, it doesn't help us out with this. So let's talk about what Steven said. If we break up the numerator over that denominator. Well, we've done that with problems before. Break up each piece there. So I would have the integral of, what is e to the 4x over e to the x? Good, e to the 3x. We're just simply subtracting our exponents. What about 2e to the x over e to the x? Just 2. And then 1 over e to the x? Yeah, 1 over e to the x, or we can write it as e to the negative x. Notice that's a lot easier to work with. Questions on that? Now let me ask you guys a question. What if it was flipped the other way around? Can I go this way and break it up like this? No. Properties of fractions, we cannot break up the denominator. What I can do is break my numerator because each piece of the numerator is being divided by the entire denominator. Here, you're not dividing by that entire denominator. Okay, so just keep that in mind for each properties of exponents. Alright. So now, if we take a look at this, we can break that up into each individual piece. So e to the 3x dx plus the integral of 2 dx plus the integral of e to the negative x dx. We do this a lot just mentally. If we would have had the integral of x squared plus 4x minus 5, we integrate each piece, right? That's all that we're doing here. So if you're able to mentally go ahead and figure out your antiderivatives for each of those, then you're done. But for those of us that can only do so much of that in our head, break it up into each piece. So now if I take a look at this one, what would my u need to be for that? 3x. And my du is 3 dx. What about antiderivative of 2 dx? What would that be? What's my antiderivative of this piece? Yeah, just 2x plus c, right? All we're doing is if I would have had the integral, again, go back to this, my antiderivative here would have been x cubed over 3 plus 4x plus c. So remember, a constant here, you're just adding on the x to it. So we don't need a u sub for that one. Alright, and then how about our last piece? What would I need u to be for this guy? Yeah, negative x. Now, once again, if you're able, because these are small u subs, if you're able to mentally figure out what the antiderivative is, because it is such a small u sub, you're more than welcome to go ahead and jump straight to your antiderivative. But I want you to go ahead and finish out this problem, whether you use the u sub or you're able to do it in your head, that's fine. But go ahead and finish out this problem, see what you do. Alright, let's see how we do this. We get 1/3 e to the 3x plus 2x minus e to the negative x plus c. Give me thumbs up if you're good with that. Okay. Now, we technically have a plus c from each of our integration pieces here. But again, a constant plus another constant is still just a constant in the end. So you can just tack that plus c on to the end. Alright, any questions on that piece? Okay. Let's go and flip it over and take a look at number 8. What do you notice is different about number 8? Has what? It has bounds! Yay, we finally have a definite integral. We're going to get a definite value in the end. Now, it appears that we still have perhaps the need for a u sub. Sine of here. That's so nice. And e to the x is inside of sine. Great. So we have e to the x times sine of e to the x. Remember, u sub is when we have a composition of functions. When there's a function inside another function. What do you guys think we should let u be? What is my inside function? E to the x. E to the x is inside of our sine. So let's let u equal e to the x. What would du be then? E to the x dx. And if we look, e to the x dx is indeed represented within my integral. So remember, you want to make sure that what you're choosing for u, its derivative is somewhere within your integral. Alright, so what else do I need to do in addition to the u du? Very good. Change our bounds here. So I need to find u of natural log of pi. And I need to do u and 0. Okay, so u of natural log of pi, and we're putting it into our u equation. So it's just e to the natural log of pi. And what would that give us? Yeah, just 5, because e natural log undo. Alright, then for this one we'd have e to the 0, which is just 1. So we actually have nicer dots. Doesn't always happen. We have nicer dots. Alright, questions so far on the setup? So now when we go through to do our integral, we have from 1 to pi. And again, e to the x dx is just the same thing as du. And now I have sine of u. This is just going back to December, how do we integrate sine of u? What's the antiderivative sign?
Negative.
Negative cosine. Okay. Negative cosine of u evaluated from 1 to pi. Do I need to take my e to the x and put it back in for you? Maybe. Do I need to take e to the x and put it back in for you? No, we already changed our bounds to be in terms of u, so don't mess yourself up and put x back in there. If my antiderivative is in terms of u, my bounds need to be in terms of u. We already went through and did the work for our bounds being in terms of u, so there's no sense in turning it back. You are welcome to take e to the x, put it back in, but you have to change your bounds to be x bounds. So you can do that, you're just creating more work for yourself. Alright, so let's get to our antiderivative here. Now you could do it where you take the negative with the cosine, or you could do negative of the antiderivative, because negative one's just a constant or coefficient there. Either way, doesn't really matter. I'm going to go and keep the negative out. So I have cosine of pi minus cosine. Okay, so just under antiderivative. And what's cosine of pi? Negative 1. What's cosine of 1? Cosine of 1. Yeah, that sounds great. So for this type of problem, if they were asking for an actual value, you would have to have your calculator. There's no way you can know cosine 1 unless you've got some skills that I don't know about. For your response, you wouldn't have a problem like this, not a calculator. You would have to take calculator first. Alright, so we would have then 1 plus cosine. I think cosine 1 is like 0.540 or something like that. Yeah, I thought so. Alright, questions with that one? Okay, so with number 10, what do you think we should let u be for that? What do you think is our best choice for the inside function? Once again, we have a lot happening. We have e to the tangent x up top, and a cosine squared x in the denominator, so we have tangent inside of e. The e and cosine squared are inside of our fraction. Steve?
Can you let u equal tangent x, or cosine would be on the bottom of that?
So if we let u be tangent x, what's the derivative of tangent again? Secant squared. Do you guys see secant squared? It's a hidden secant squared. Good. Alright, so go ahead and try number 10 with u being tangent x. Very good. You're speaking a new language? Yes. Yeah, do you have your agenda with you? Take this guy. No.
Did you think about that?
Okay, I'll think about it. No.
So yeah.
Sometimes I do. You know, they're looking suspicious. Alright, so this one ends up not being very bad. So we have let u be tangent x, and as we said, du is secant squared x dx, which we see represented there. So when we do our u sub, we get the integral of e to the u du, which gives us e to the u plus c, which is just simply e to the tangent x plus c. Questions with that? Is that a question? Yeah, just a movie. Okay. take a look at, let's take a look at 14. So 14, once again, we have e to the square root of x on top. So square root of x is inside e. But e is inside that fraction. And in our denominator, we have 2 root x. What should we let our u be? What do you guys think? Root x? Alright, so if we let u be root x, which is the same thing as x and positive, what would du be? 1/2 x to the negative 1/2 dx. Do I see that x and negative 1/2 represented in my integral? Yeah, because the x and negative 1/2, I could rewrite this as 1/2 root x dx. So we have that represented here. Actually, we even have that 2 piece with it. Ah, it's going to be such an easy integral. What else do I need to do, though, before I continue? Change our bounds. All right, so go ahead and try number 14 there. Keep in mind you need to change your bounds, see what you get. Alright, so I went through, we should have gotten an answer of e cubed minus e to the first, is that right? So what you guys, questions on that? Is that e squared? Can we simplify that? It's e squared.
No.
Why not, Travis?
Because that would have to be e over e to the first.
Very good. So remember, we subtract exponents when we're dividing like this. That's a good way to put that. Now, AP multiple choice, it's very possible that they could present the answer like this. They might not. And if they really wanted to, they could even present the answer like this. So I feel like they're probably not going to do this last one, but I wouldn't be surprised if there's no one. So just be aware that sometimes multiple choice, you have to manipulate your answer there. But this is our answer. These are just manipulations of it. Nick, did you have a question?
I'm just wondering, this isn't like e to the first part of this one. I mean, isn't it just e?
Yeah, so you wouldn't have to write that one there. You could just do e cubed minus e would be fine. All right, questions on that? Okay, let's take a look at our natural logs. Alright, so it says integrals of the natural logarithm. Technically, we're not integrating natural log. We are just doing integration that deals with natural log. So we in Calc AB do not integrate natural log by itself. Alright, so we are not doing that, but these are integrals that might result in a natural log. So keep in mind, last class we learned that if we have the natural log of x, is its derivative 1x. And once again, if there's something more than x, we have to follow chain rule with it. So then if I have the integral of 1/x dx, what is that going to equal? Natural log of x plus c. Because once again, taking the derivative of this should get me back to here. Now there is a technicality we talked about last class that we do need to consider also for our integrals. If we think of our natural log graph, what is the domain of my natural log graph again? 0 to infinity. I cannot have any negatives within here or 0. I have to have all the positive numbers. So what can I do to this x to guarantee that it's going to be positive numbers only? Absolute value. So our antiderivative of 1 over x is actually natural log of the absolute value of x. That guarantees that we are only getting positive values before we take that natural log. And once again, u sub still applies when it's that composition of functions. So just make yourself note u sub for composition. Okay, so let's take a look at number 1. 4 over x dx. Does that look exactly the same as this guy here? It's pretty close. That pesky 4 is in our way. What can we do with that 4? Yeah, just bring it out in front. And what's the antiderivative of 1 over x? Natural log of the absolute value of x plus c. And once again, you can multiply that forward to the constant, but it's not necessary.
Put the value or not?
It is absolutely essential you put that absolute value. If you do not have the absolute value, it will be wrong. Yes?
Is there a reason why we can't bring it as back into the top and get rid of the extra negative or itself?
Ooh, great question. I'm so glad you asked. So Isaka said, well, isn't this just the same thing as 4x the negative first dx? Do you agree that we could rewrite that?
Yeah.
Okay. So again, we know we can pull our 4 out in front. But if I try to apply our reverse power rule, what do we do? If it was x squared dx, what do we do with our power there? We add 1 to it and divide by our new power. Alright, so if I add 1 here, what do we get for our new power? Yeah, we have x to the 0th power over 0. Maybe. And we have that issue of dividing by 0. So that's the reason why we can't do this. So natural log is actually imperative. That's a very good question. So if you forget that it was natural log and you tried this, you would see that issue there where you would end up being dividing by 0. But that is why we cannot apply the power rule there. Very good. So our power rule actually applies for integration for all powers except power of negative. Oh. What did you say? Yep. Right there. Okay, so again, make sure you have that absolute value around your argument. Otherwise, alright, questions with that one? Okay. So with number 2 here, we have something more than just x in our denominator, so we are going to have to do a u sub with this. So I'm just going to go and let u be that entire denominator, because then I have 1 over u, and we know the antiderivative of that. So let's let u be 5x minus 2. What would my du be? 5 dx. Do I have the 5 already represented here?
No.
Nope, so let's go ahead and divide that over. So 1/5 du equals dx. Alright. So again, here's an example of when we would need to use u sub. Alright, so we'd have the integral 1 over u dx is 1/5 du. And what is my antiderivative of 1 over u? Natural log of the absolute value of u. And again, for our final answer, we need to put that x back in. 5x minus 2 plus 3. Again, this is kind of a smaller u sub, so if you're able to recognize that, hey, chain rule would have required multiplying by 5, so to counteract that, I would divide by 5. You're able to jump straight to answer that question. Any questions on 1 or 2? Alright, so 4 is a little bit more complicated. We see we have a 7x up top, not just a constant. And we have x squared minus 4 in our denominator. We already talked about we cannot break it up 7x over x squared minus 7x over 4. We could factor the denominator, but that's not going to help us out at all. What do you guys want to do? What are your thoughts? Besides nothing, you must do something. If I try to u sub, what type of u sub should we do? What would we let u be? That x squared minus 4. How about the whole thing? Let's go with the whole denominator. Because we know that if we're left with just that u in the denominator, that we can do our natural log for our antiderivative. but let's make sure that it gets rid of the x up there. So if we let u be x squared minus 4, what would my du be? 2x dx. Is that x represented in my integral? Yeah, we've got that x there. So it's good. We see its derivative is represented. Now we do have to deal with our coefficients a bit. I don't have a 2 represented, so I want to go ahead and divide that on the other side. So 1/2 du is x dx. So we've got this whole piece represented. I don't need that 7 though, so let's go ahead and pull that out in front. So x dx is just 1/2 du. I'm going to go ahead and bring that 1/2 in front to make it easier to work with. And then I have x dx is du. And x squared minus 4 is just. Alright, and then now it's a much easier integral to work with. So 7/2, antiderivative of 1 over u is natural log of the absolute value of u plus c. So we have 7/2 natural log of the absolute value of x squared minus 4 plus c. And that's your final answer. Alright, questions with that? Okay, so again, sometimes it's a little disguised and needing to use that natural log for antiderivative, because here we just see a bunch of polynomials, but like we talked about, there was no factoring that could have been done or breaking up algebraically. So doing that u sub setting the bottom equal to that u value, its derivative was represented there, allows us to then do integral. Let's say that this was x squared plus 4 inside my argument there. Would I technically need the absolute value? It was x squared plus 4. No, because x squared plus 4 is always positive. Now, it's not going to hurt to put the absolute value, but if you see it left off, that's probably why. Here, though, x squared minus 4 definitely can have a few numbers. Right, questions before I take a look at this next section? So another thing I want to caution you with is to not force natural log when it's not necessary. Now that we learn natural log, students tend to see a fraction and be like, oh, the entire denominator is going to be my u and it's automatically natural log. That's not always the case. So let's take a look at number 5. This is a type of problem that we would have done before. We see we have x over the square root of 16 minus x squared. Again, we have 16 minus x squared is inside the function square root, but then both pieces are also inside our fraction. So let's let u be this completely inside piece here. I'll just write it.
So if you only put the absolute value when?
I just always put it negative. Alright, so let u equal that inside piece. What would du be? Negative 2x dx. And do I see that x represented up top? Yeah, it's right there. Alright. But I need that negative 2 over, so I'm going to go and write negative 1/2 du equals x dx. Alright, so now when we do our u sub with this, we have the integral. X dx is negative 1/2 du, so I'm going to bring that negative 1/2 out. Then I just have 1 over square root of u to u. Are we okay with this u sub here? Alright. So now don't be tempted to say, alright, so that's going to be the antiderivative is natural log of the absolute value. That's not the case. Take a look at how else we could write this. Let's just use the negative 1/2. Natural log is used when we have that exponent of 1 in our denominator, right? So we had 1 over u. 1 in our denominator, 1 in our denominator. And up there it was also 1 in our denominator. If it's something more than just 1 in our denominator, then we just use our normal power rule techniques. So here I would just go ahead and add 1 to the exponent. So I have negative 1/2. Add 1 to my exponent. U to the positive 1/2. And divide by my new exponent. So I have 2. Notice natural log did not take a play in this at all whatsoever. It didn't have any part in it. So again, natural log is used when it's 1 over power of 1. But otherwise, it's just your normal power rule. And if you're not sure, try the power rule. It won't work if you have to use natural log. Logan, do you have a question?
Why is it two used for one half?
So we add 1 to our exponent and divide by the new exponent. When I divide by 1/2, same thing as multiplying by the reciprocal. Alright, so let's go ahead and I'm gonna make myself go crazy and go this way. Let's clean up. So our 2's would reduce to negative. And let's put our x back in. So negative, this is square root. And u was 16 minus x squared. Plus. And there's our answer there. So again, it's just normal power rule. Right. Questions on that?
So the C doesn't get negative.
Again, Nick, you can multiply this out to the C, but it's not necessary because it's just representing a constant. If you do on a first round, so that's perfectly fine. Alright, other questions with that problem? Okay. So I want you to go ahead and try number 6 here.
Number 6.
Again, don't force the natural log. Sometimes you need it, sometimes you don't. Once you do 6, go ahead and try number 7. And in a moment, I'll go and put up both answers and see if you get to this the same thing. Alright, so I put the answers up there, so as you do number 6 and 7, check to see if you got the same thing, see if you can get to that correct answer. Yeah, so you can see that. Alright guys, so for number 6, make sure you did not lose your 1/2 when you did your use up. And also we had to multiply by the reciprocal of our new exponent, so we had 1/2 times the 3/2, which is what gives 3/2. For number 7 here, what did we let u equal? ln of x, because that was our inside function. Alright, so your homework is to do the odds in this packet, the odds, and next class we'll do more practice with this.
Number 7,
Because you didn't do the antiderivative of 1/n.
So, like, I've been having trouble.